Welcome to this explainer, everyone. Let's get right to it. Today, our mission is clear. We're going to absolutely demystify the parabola. If you're prepping for competitive engineering exams like the JEE, you already know conic sections can feel like this endless maze of formulas. Well, today we're arming you with a strategic blueprint for success. We're breaking down the geometry, the algebra, and those high-yield exam patterns so you can tackle these problems with total confidence. Okay, let's dive into this. We really need to shift our mindset away from messy, brute force calculations. I want you to start seeing the parabola as a perfectly balanced, mathematically elegant structure. Because when you actually understand the underlying architectural mechanics, the formulas just naturally fall right into place. And that is going to save you precious time on the exam. So here is our attack plan for today. First, the anatomy of the parabola. Second, the four standard forms. Third, the power of parameter t. Fourth, tangent and normal mechanics. Fifth, the chord ecosystem. And finally, number 6, we'll wrap up as a high-yield exam strategist. All right, Section 1, Anatomy of the Parabola. Let's establish those foundational geometric rules. Every parabola you'll ever encounter is built on these absolute non-negotiable building blocks. You got the focus, which acts as your fixed gravitational center. You have the directrix, your fixed straight baseline. The vertex is that point on the curve closest to the directrix, sitting exactly halfway between the focus and the directrix. And running right perpendicular to the axis of symmetry, straight through the focus, is the latus rectum, which always has a total fixed length of 4a. So, the crucial point is right here. Eccentricity, or E, is always exactly 1. The literal definition of a parabola is that any point on the curve is perfectly equidistant from the focus and the directrix. I'm telling you, forgetting this eccentricity rule is a fatal, yet incredibly common trap in exams. It is not less than 1, it's not greater than 1. For a parabola, E strictly equals 1. Just lock that in right now. Section 2, the 4 standard forms. Let's look at the basic orientations. All right, this is your standard forms matrix. You've got parabolas opening right, left, up, and down. Now the linear variable, the one that isn't squared, that tells you exactly which axes the parabola wraps around. And here is a massive strategic tip for you. The constant A must always be strictly positive. The directional sign, that's already built right into the equation's framework. Never, ever plug in a negative value for A, or your entire geometry will completely collapse. Moving on to Section 3, the power of parameter t. This is where we upgrade from basic geometry to some serious algebraic machinery. I really want you to let this sink in. Parameter t reduces a 2-variable locus puzzle into a single-variable algebraic machine. When you are staring down a seemingly impossible locus problem with moving points, t is your ultimate secret weapon. It literally simplifies everything. And this brilliantly illustrates exactly what I mean. Think of the parameter t as a skeleton key. That central hug coordinate at squared, 2at, effortlessly unlocks multiple problem-solving paths. Whether you need to derive a tangent slope, map out a normal line, or lock down a focal chord, everything radiates perfectly from this single parametric point. Because under intense exam time pressure, you simply do not have the luxury of juggling x and y simultaneously. By substituting x and y with our parameter t, you instantly drop an entire dimension of complexity. For y squared equals 4ax, any point is just at squared, 2at. This is the absolute fastest engine for writing equations and solving intersections when that clock is ticking against you. All right, Section 4, tangent and normal mechanics. Time to apply that t parameter to some heavily tested exam concepts. When you're tasked with building a tangent, you basically have 3 distinct architectural tools at your disposal, and you have to choose wisely. You have the Cartesian tool, the parametric tool using t, and the slope tool using m. Your choice depends entirely on what specific information the exam question throws at you. Let's compare the big 2. The Cartesian t=0 method is your best friend, but only when the point you're given lies perfectly on the curve itself. It's just a straight substitution. But if the problem involves slopes, or if the points are floating out in external space intersecting the parabola, you must immediately switch to the parametric form t equals x plus at squared. It is vastly more flexible. Okay, strategist, time for some rapid-fire, high-value targets. You've got to memorize these shortcuts. If y equals mx plus c is a tangent, then c strictly equals a over m. The point of contact? Exactly. A over m squared, 2a over m. Need a pair of tangents from an outside point? Boom, use SS1 equals t squared. And here's a favorite JEE trick. If two tangents are perpendicular, do not waste time calculating their intersection. They will always meet directly on the directrix, x equals -a. Now, what's really interesting about this slide is the elegant simplicity of normal mechanics. A normal is just the line perpendicular to your tangent at the point of contact, right? But when examiners test normals, they are usually hunting for one very specific phenomenon. Here are your normal formulas, but I want you to look really closely at the parametric form, y equals -tx plus 2at plus at cubed. Because that is a cubic equation in terms of t, it means from any given external point, you can draw a maximum of 3 normal lines to the parabola. And here's the direct, highly tested JEE result. If those 3 normals hit the curve at parameters t1, t2, and t3, their sum, t1 plus t2 plus t3, must perfectly equal 0. Absolutely memorize that condition. On to section 5, the chord ecosystem. Examiners love to test your conceptual clarity here. Let's distinguish between these setups. The chord of contact uses the formula t equals 0. The chord with a given midpoint uses t equals s1. Now, the algebra might look somewhat familiar, but the geometry is entirely different. T equals 0 connects tangent points from an external observer, while t equals s1 locks a chord around a specific center point inside the curve. Do not mix these up. Now, if a chord happens to pass right through the focus, it becomes a focal chord, and that triggers some special conditions. The parameters of its endpoints lock into a strict relationship. T1 times T2 equals -1. Furthermore, the segments of that focal chord relate to A via a strict harmonic mean. 1 over SP plus 1 over SQ equals 1 over A. I'm warning you right now, exams will absolutely try to trick you into using an arithmetic mean here. Don't fall for it. Let's move to and see how this builds into our final phase. Section 6, High-Yield Exam Strategist. Let's talk tactical execution. So what happens when the vertex isn't at the origin, but shifted to some random point h, k? Please do not memorize a dozen new messy formulas. Just use the shifted vertex protocol. Step 1, substitute and standardize the environment into capital X and capital Y. Step 2, solve the problem using the easy standard matrix we learned earlier. And step 3, revert your answers back to lowercase x and y. It is an entirely foolproof system. Keep your threat detection radar highly active, folks. Watch out for these 5 major traps. Trap 1, axis confusion. Always double-check which variable is squared. Trap 2, writing +1 instead of -1 for that focal chord condition. Trap 3, accidentally calculating the latus rectum as just 2a instead of the full 4a. A mistake so incredibly common, examiners basically bank on you making it. Trap 4, letting the eccentricity drift from exactly 1. And trap 5, trying to brute force a shifted parabola instead of just using our substitution protocol. We have covered some incredible ground today. You now possess the precise architectural blueprint of the parabola. You hold the skeleton key of parameter t. You know exactly how to bypass those tricky traps and leverage the high-yield formulas. The geometric mechanics are completely on your side now, so the only question left is, are you ready to take this knowledge, architect your GE success, and absolutely dominate your next practice exam? Go get 'em!